Welcome to the discussion on the topic analysis of beam in pure bending. This is the part of content in the unit 3 flexural stresses in beams, right? This is the no uh, part of the syllabus in the strength of materials 1 course. Now let's look at what we are going to learn in this. In this analysis of beam and pure bending, what I am going to do is I am going to take uh, a kind of a beam that is subjected to bending moment, pure bending moment, and for that, know how to calculate design forces, right? So for that, no, you may be sometimes required to calculate the bending stresses, or sometimes you may be required to calculate the loading capacity of the beam, right? In this, but there are, you may be even to sometimes you need to calculate the span of the beam, how much span of the beam you know that the beam can require in order to carry the loads, right? So if you look at here in this particular discussion, we will be dealing with, so if at all we want to know if a member is beam is subjected to pure bending and you are required to calculate the allowable bending stress, right? So that is one of our target. The other one is now if you want to calculate the load carrying capacity, what is the maximum load the beam can carry, right? If the beam is subjected to pure bending and you are expected to look at the maximum load carrying capacity, right? In that case, this particular topic is not relevant, right? For that sake I am discussing this. So let us take a practical situation, a problem, then you can better understand this. Remember, our target is, for one case we are going to handle allowable bending stress calculation. In another case we are going to see what is the load carrying capacity of the beam which is subjected to pure bending, right? Before proceeding, remember, we are going to use the pure bending, right? Our beam is no, our concept is pure bending. So what is the governing differential equation for that? M by I is equal to sigma or f. Some people write f, some people write, it doesn't matter, like any difference. So you can use any symbol for sigma for stress. So this is the governing differential equation that we are using. Of course E by R is there not in the equation, but we are not going to use that here. Only these terms are sufficient enough. So in one case you are expected to calculate the sigma, this is your goal, and the other case you may be required to calculate the load carrying capacity, which is part of your M. Bending moment consists of two terms, right? One is the span, that is L, another one is load. These two are required, right, for the calculation of the bending moment. You require span, you require bending moment, sorry, load, right? Then you will get getting the bending moment. So now let's forward and take a numerical example. Here is a beam, a cantilever beam is there, having a length of 2 meters, fails when a load of 2 kilonewton is applied at the free end. If the section is having these dimensions, find the stress at the failure. So now let's see, let us represent that what was given. There is a cantilever beam and the cantilever beam is having a load of 2 kilonewton at the free end. This is your load acting here and this span is 2 meters. Okay, for this case this cross section was also provided to you, 40 by 60. 40 is the width, usually width will be less, right? And 60 is the depth of the beam. Okay, so this was the situation presented to you. There is a load acting 2 kilonewton at the free end and this is a cantilever beam. Okay, so first of all try to learn, see, practically speaking, the solution lies in the problem itself. Okay, when you are applying, when you are applying when you are going for the solution, always important to look at the question very carefully, because the solution lies in the question itself. So if you look at here, if you are completely understanding or thorough of this, your solution is right away in front of you, right? So now what you are supposed to calculate? Stress at the failure, say sigma max. Maximum stress reaches, it fails, right? So sigma max is what your target is. According to our formula, just now I have written, right? What is sigma becomes? It becomes m by I times y. So go to that, m by I times y. M by I times y. So here let's look at whether things are available to us or not. So for calculation of m, what is required for us? If you want m, you require two things. One is the load, another one is the span. Is available. Cantilever beam, right? Max, if you are using, if you want to calculate max, your m should be max value, your y should be max value, because I require max. So maximum bending moment you have to take, and you have to take y max. Y max in the sense from the neutral axis, the farthest fiber that is possible. So this is your y, right? So straight away everything is available here. Let's say you want m. What is the formula for the maximum bending moment? Maximum bending moment in a cantilever beam occurs at the support, right? That value is 2 times WL square by 2, right? So 2 times 2 square by 2, because load is 2 kilonewton acting here, and your span is also 2 meters. So this is your final value. Your what you are getting around, no, to cancel, what you are getting 4 kilonewton. That's the moment. So moment is available with you. 4 times 4 is in kilonewton, right? So if you want to get the stress is generally expressed in newton, so better write in newton mm. So 1 kilonewton meter is nothing but 10 to the power 6 newton, 10 to the power 6 newton mm. So you got the moment value with you. So next thing you require is I. It is also available here, because I is no requires I calculation requires only BD, right? You have I with you for a rectangular section. This is a rectangular section 40 by 60 is nothing but you require, loading is vertical, right? So I already told moment of inertia should always be taken in a direction perpendicular to the application of the load. Load is in y direction, therefore xx you require 40 times x 60 cubed by 12, right? This is your moment of inertia. And then we require y. Y is simply maximum farthest fiber distance from the neutral axis. That is nothing but your d by 2. D is 60, so 60 by 2 is your value. uh, so now you got the values of say m, I as well as y. So you are right at the solution now. So you got this m value, got this I value, and you got this y. So you simply substitute that, you will be getting the solution straight away, right? Look at that. So your moment is 4 kilonewton meter, which can be converted into 4 times 10 to the power 6 as we have written earlier. And if you work out this, it will be around 7.2 times 10 to the power 5 mm power 4, and you have the y max value. Okay, so all three are ready, just put in the formula straight away. That's the your solution part. So got sigma as m by I times y. This is the final solution. Okay, as I said earlier, if you are thorough with the complete information given, solution is straight away in your front. Okay, in one step you get the solution, right? Next, The next topic that we are going to in the in our right in the beginning we have discussed that another topic that we want to deal is about the analysis of the beam and pure bending, where we require to calculate the load. What is the amount of load carrying, maximum load carrying capacity we have targeted, right? So here such kind of problem was selected. So we have a rectangular beam having so and so deep and having so and so wide, right? Is simply supported over the span. So here if you represent the beam here, you have been given a simply supported beam, which means having one roller and one hinge. It doesn't matter whether it is on the left side or right side, what location doesn't matter. So but basically it is a simply supported beam. And what was the dimensions of the beam, that was also given. Okay, so here you have a beam having a size of 200 and depth of 300. So this is your 200 width and depth as 300. Okay, so you have these dimensions, and the span was also given, right? 8 meters. Now there was a, if there is a load, so this is what he is asking. There is a load kept which is unknown now, say W kilonewton meter. I kept a load and he is asking what is the maximum I can, maximum load I can apply on this beam. Okay, so that was the question. So look at, these are all the, it has been given, right? LBD, length is 8, the breadth is 200, this one is 300, and you have been given also the permissible bending stress, okay, 120 Newton, and you are expected to calculate the UDL intensity, right? Again we are using the same formula, right? What was this? We are now supposed to calculate the value of load. So load is related to the term M, because M depends upon two factors. One is the load carrying capacity, another one is the span. You have been given the span, asked to calculate your W. So your equation, you can write M is your desired quantity. So M by I equal to E by sigma y, right? M sigma by y equal to M by I. So bring the terms I that other side, right? So what you will be getting, sigma by y is into y. This of course I by y is also called section modulus. I by is also called section modulus. As of now, our goal is to get W, which is function of your W and L. For a simply supported beam, when there is a UDL, what is the amount of maximum bending moment that is caused? It is basically, you will be getting a shape of parabola with a maximum value of W L square by 8. This is your bending moment. This is required because M term refers the maximum bending. So that is your maximum value. So M is now in our hands, but there is an unknown. Remember, the unknown is W. W times span is here 8 meters, right? And is 8 meters, 8 square by 8. Keep that aside. Okay. Then sigma was anyway known to you. Y is what is y here? So the y value is also unknown, right? Y was is known to you. Yes. Yeah, depth was given. Sorry. What was, yeah, depth, it is known to you. So 300 through 100. So y is easy now. Y is nothing but 300 time by 2, because that is the maximum distance from the neutral. This is the neutral axis, for example. Sorry. This is the neutral axis. From the neutral axis, your distance will be d by 2. This is 300 total. It is 150. So this 300 by 2. So y is also known to you now. Y is known. I is also known because it is simply BD cube by 12. I is also again here Ixx, right? Because the loading is in y direction. Perpendicular direction we require the moment of inertia. 200 times 300 cube by 12. Here one small information one can just to reduce the calculation one can substitute it in centimeters and reconvert into mm. Okay, just to computational, in order to reduce the computational effort one can do that, right? So simply you can write 20 into 30 cube by 12 and you get some value, convert in from, you will be getting in centimeter power 4, later on convert into 10 to the power 4 mm power 4. That can be done. Say just for the sake of memory. Similarly here 30 by 2 becomes 15 centimeters is equal to 150 mm. That can be done. Anyway, now you are done with all the terms required. I is known, y is known, sigma was anyway provided. So only unknown here will be w, right? So you can find out only one known, unknown, one equation you can get it. Let's look at how you get that solution. So you got this, right? 8w, same value we got here, 8w, because 8 1 8 get cancelled, 8w. But remember the units here, assuming that the load is in kilonewton and the span anyway it is in meters, right? We got the value of kilonewton meter. You can convert into Newton mm by multiplying this particular value with 10 to the power 6, because 1 kilonewton meter is nothing but 10 to the power 6 Newton mm. Okay, we got that I value we got, right? So as I told you, either you can do 30 times 20 cube. Sake of simplification I am just doing this, is it calculated in terms of centimeter, later on will be converted, right? So if you calculate that, you can simplify. This is 3 by, right, 4, so that is 4 times it goes, and here it is 2 cube means 8, so 8 times 1000 or 10 to the power 4 you can say, because here it is 1000, it is one more zero here, 10 to the power 4, right, divided by, what is this value here, we got 4. So 4 goes 2 times, you will be getting 2 to 10 to the power 4. This is in 10 to the power 4 centimeter power 4, which can be converted to mm power 4 by multiplying with one more 10 power 4, then becomes it is 10 to the power 8. That's all. Okay, like remember here I think we have taken depth as 150, but here the information was slightly misrepresented, that is why the mistake came. 200 was depth, so sorry, this dimension is, because this mistake happened because I have not read it the problem in a proper complete detail. So I just represented 200 way. Generally what happens is depth will be more, but in this case it is specific, so because of this we got a mistake. So this is not 300 here, you will be getting 200. Okay, except that everything is fine. So you get that value, simply put it here. The only unknown is that you will be getting, this is the value, Newton per mm, because you have converted everything in newtons and into mms, so you will be getting finally 30 Newton per mm, which is same as 30 kilonewton per meter, same as 30 kilonewton per meter. That means it can handle a load of 30 kilonewton per meter over a span of 8 meters, so that the beam material will not be subjected any more stress beyond 120 Newton per mm square, right? So this is the problem on how to get and calculate the maximum loading carrying capacity of a beam subjected to pure bending. The other one is how to calculate the allowable bending stresses in the beam subjected to pure bending concept. Okay, that's all about this problems or analysis of a beam in pure bending. Right?